Definition and identification of irrational numbers. Hello, everyone. Today, we are going to begin a new topic, the definition and identification of irrational numbers. Now, before we dive into the new material, let's start with a quick introduction to set the stage. In your previous studies back in grade 9, you were introduced to the concept of rational numbers. It is vital that we have a solid grasp of that concept before we move forward. To understand what makes a number irrational, it is essential that we first recall exactly what a rational number is. As you may remember, a rational number is any number that can be expressed as a fraction, p over q, where p and q are both integers, and q is not equal to 0. With that definition fresh in your mind, we can now introduce our main subject. You can think of irrational numbers as essentially the opposite of rational numbers. While rational numbers cover many points on the number line, they don't cover everything. Irrational numbers are the numbers that fill in those tiny, infinite gaps on the number line that rational numbers simply cannot occupy. Over the next few slides, we will look at how to formally define these numbers, and more importantly, how you can identify them yourself. Definition of irrational numbers. Now that we've established that irrational numbers are essentially the opposite of the rational numbers you studied last year, let's look at the formal definition. A number, let's call it C, is classified as irrational if it cannot be expressed in the form p over q, where two specific conditions must be met. First, both p and q must be integers, meaning they are whole numbers. And second, q cannot be equal to 0. If you find it a bit difficult to wrap your head around that formal notation, don't worry. In simpler terms, if you find that you simply cannot write a number as a simple fraction using two whole numbers, then that number is irrational. In the next slide, I'm going to show you a much more practical way to identify these numbers just by looking at their decimal expansions. Identification via decimal expansion. Now that we have established the formal definition of an irrational number as something that cannot be written as a simple fraction, let's move on to a much more practical method for identifying them. One of the most effective ways to spot an irrational number is by looking closely at its decimal representation. To really understand this, we need to compare them to what we learned in the previous slide about rational numbers. For rational numbers, the decimal expansion is predictable. It will either terminate, meaning it comes to a complete stop, like 0.5, or it will repeat in a regular, predictable pattern, such as 0.3 recurring. Irrational numbers, however, behave very differently. Their decimals are non-terminating, which means they never, ever end, they continue infinitely. But there is a second crucial part: they are also non-recurring. This means they never settle into a repeating cycle or a fixed block of digits. So, as we move into the next slide, I want you to keep this distinction in mind. It's not just about the decimal being long, it's about the lack of a repeating pattern. Example of non-terminating, non-recurring decimal. Take a look at this decimal number: 0.10110111101110, and so on. I want you to carefully observe the sequence of digits appearing here. You will notice a specific structure. We see a single 0, followed by a single 1, then another 0, then 2 1s, then a 0 again, followed by 3 1s, then a 0, and then 4 1s. Now, this is a very important distinction to make. While there is clearly a logical pattern occurring, specifically, the number of 1s is increasing each time, there is no fixed block of digits that repeats identically. In our previous slide, we learned that for a number to be rational, it must have a repeating cycle, like 0.3 recurring. But here, because the pattern is constantly changing and never settles into a repeating loop, it fails the test for rationality. Therefore, because this decimal is both non-terminating, meaning it never ends, and non-recurring, meaning it never settles into a repeating cycle, we can conclude that this is an irrational number. This leads us directly into our next slide, where we will look at more common examples of irrational numbers you'll encounter, such as square roots. Now, let's move from the theoretical definition we just discussed to a concrete visual example to help you identify these numbers in practice. Examples and analysis. In the next few slides, we are going to examine different types of irrational numbers in detail, looking at specific examples to help you master how to identify them in your exams. Now that we have established the formal definition and the decimal characteristics of irrational numbers, let us move on to some practical applications. Square roots of non-perfect squares. Now that we understand the general concept of irrational numbers through their decimal patterns, let's look at a very common way you will encounter them in your math problems: square roots. A great rule of thumb to remember is this: if you have a positive integer that is not a perfect square, meaning it isn't a number like 1, 4, 9, or 16, which we know are results of squaring whole numbers, then its square root will always be irrational. Let's walk through two examples to see this in action. First, let's look at the square root of 2. To identify if this is irrational, we follow 3 simple steps. Step 1, we check if 2 is a perfect square. Since there is no whole number that, when multiplied by itself, equals 2, we can conclude it is not a perfect square. Step 2, if we look at its decimal value, we see it is approximately 1.4142136, and so on. Step 3, because these decimals never end and never settle into a repeating pattern, we can confirm that the square root of 2 is indeed irrational. Next, let's examine the square root of 15. Following our process again, step 1, we check if 15 is a perfect square. It isn't. Therefore, following the logic we just discussed, we can conclude that the square root of 15 cannot be expressed as a simple fraction, or p over q. This makes it an irrational number. As we move to the next slide, we will see that this concept extends beyond just simple square roots to include famous mathematical constants. Mathematical constants. Now that we have explored how square roots of non-perfect squares behave, let's move on to a different category of irrational numbers. Some numbers aren't just results of square roots. They are actually defined by geometric properties and are inherently irrational. Take, for example, the most famous mathematical constant, pi. To give you some real-world context, pi represents the ratio of the circumference of a circle to its diameter. No matter how large or small the circle is, this ratio always remains the same. Now, let's perform a quick analysis. In your previous math classes, you have likely used 2/7 or 3.14 as a way to calculate area or circumference. It is very important to remember that these are only approximate values used for convenience. If we look at the actual value of pi, it begins as 3.14159265, and it continues forever without ever settling into a repeating pattern. Because it is non-terminating and non-recurring, we can conclude that pi is, indeed, an irrational number. In the next slide, we will see how we can combine these types of irrational numbers through operations like division. Combinations of irrational numbers. Now that we have looked at individual irrational numbers like square roots and mathematical constants, let's see what happens when we combine them. It is important to note that numbers involving fractions of square roots can also be irrational. Let's examine this specific example: negative square root of 2 all over square root of 3. To determine if this is irrational, we can follow a simple 3-step process. First, identify the components. As we discussed in our previous slides regarding non-perfect squares, both the square root of 2 and the square root of 3 are irrational numbers. Second, consider the ratio. When you have a ratio of 2 such square roots, provided they don't cancel each other out to form a perfect square, the result is a decimal that is non-terminating and non-recurring. Finally, based on these steps, we can conclude that negative square root of 2 over square root of 3 is indeed an irrational number. As we move to the next slide, I want you to keep this in mind, because there are a few common mistakes students make when trying to identify these types of numbers. Common mistakes to avoid. First, let's talk about a very common confusion regarding pi. Many of you have been taught to use 22/7 as a substitute for pi in your calculations. Because 22/7 is a fraction, it is a rational number. However, it is crucial to remember that 22/7 is merely a rational approximation used for convenience in school problems. It is not the exact value of pi. As we discussed in the previous slide, the actual value of pi continues forever without any repeating pattern, making it truly irrational. Second, be careful not to assume that every number under a square root sign is irrational. While we saw earlier that the square roots of non-perfect squares, like the square root of 2 or the square root of 15, are irrational, this isn't a universal rule. For example, if you see the square root of 4, you must remember that the square root of 4 simplifies exactly to 2. Since 2 can be written as the fraction 2/1, it is a rational number. So, my advice is to always check if the number under the radical is a perfect square before you jump to a conclusion. Finally, there is a subtle difference between a pattern and a recurring decimal that often leads to mistakes. In our earlier example, we looked at the decimal 0.1011011110, and although you can see a logical growth pattern there, it is not considered recurring. In mathematics, recurring specifically means that a fixed, identical block of digits repeats infinitely, such as 0.12, 12, 12, and so on. If the pattern changes or grows, even if it follows a rule, it is not recurring, and therefore the number remains irrational. Now, before we wrap up today's lesson with our final summary, I want to pause and address some common pitfalls. Even the best students often fall into these 3 traps when identifying irrational numbers, so please pay close attention here. Keep these distinctions in mind as we move into our final key takeaways. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways to ensure everything we've discussed today is clear. First, let's revisit the formal definition. Remember, an irrational number is defined by what it cannot do. It cannot be expressed as a fraction, where p and q are integers, and q is not equal to 0. If you can't capture the number as a simple ratio of 2 whole numbers, you are dealing with an irrational number. Next, let's look at their decimal nature. This is a very reliable way to identify them. Unlike the rational numbers we looked at earlier, which either end or settle into a repeating loop, irrational numbers are always non-terminating and non-recurring. This means the digits go on forever and never settle into a predictable, repeating cycle. Finally, let's summarize how to identify them in practice. You can use 3 main indicators. First, the square root of any non-perfect square is always irrational, so, while the square root of 4 is just 2, the square root of 2 is irrational. Second, keep an eye out for mathematical constants, the most famous being pi, which is inherently irrational. And third, be careful with decimals that seem to have a pattern. If the pattern involves a changing sequence of digits that never repeats a fixed block, like the example we saw with the increasing number of ones, then that number is indeed irrational. I hope this summary helps solidify these concepts. Keep practicing, and I will see you in our next session.